So we've just determined the parametric form for a point on a parabola y squared is 4ax. We're now going to call that from now on in at squared 2at. Now let us determine the equation of the tangent at that point. We're going to do this in the same way that we do it for many of the other shapes, and we've actually already done this in what we needed to get the parametric form. So let me remind you, we ended up showing that y equal x over t plus at is the equation for the tangent. But let's suppose that we haven't done that and we literally start with the pair of parametric equations at squared 2at. So first of all, we can determine the gradient of the parabola at that point. We can use the chain rule, so dy by dx is dy by dt times dt by dx, which is dy by dt over dx by dt. If we substitute for y as 2at and x as at squared into that, we can easily show from this chain rule that dy by dx is 1 over t. Again, reinforcing the fact that the gradient of the tangent at the point at squared 2at, 2y squared equal 4ax is just 1 over t, 1 over the parameter t. Okay, let's suppose we now want to work out the parametric form for the equation of the tangent to that point. So let's take p x comma y as a general point on the tangent and at squared 2at as the point on the parabola where the tangent touches it. So first of all, because we know the gradient of the tangent is 1 over t, but because we also know that the line segment from the point to p has gradient which is y minus 2at over x minus at squared, then these two things are equal, and on rearrangement we get this standard equation in the box that we will use many times, which says that the equation of the straight line y in terms of x for the tangent at the point at squared 2at on the parabola is x minus ty plus at squared equal 0. And if you rearrange that, that's exactly the same as this equation here in the box. You can check that. So from now on in, we're just going to use this expression and just take it for granted. Now if you wanted to look at the Cartesian form for the same tangent, then we could take y squared is 4ax, differentiate with respect to x implicitly, and then work out that, say, at the point x1, y1 in Cartesian form, that the gradient dy by dx is 4a over 2y, so at x1, y1 is 4a over 2y1. In other words, this. Again, if xy is a point on the tangent, x1, y1 is a point on the tangent but on the parabola, then this represents the fact that the gradient of the line segment from x1, y1 to p is the same as the gradient 2a over y1. If we rearrange that as shown here in exactly the same way as when we had the circle, we could eliminate the equation for the circle. We also know that y1 squared is 4ax1 because x1, y1 lies on the parabola. In other words, we can get rid of the y1 squared and we get this Cartesian equation. We won't use that anywhere near as much as the form involving t, the parameter. And again, you can quickly check that if you substitute for y1 as 2at and x1 as at squared, you get the same parametric form as shown before. Now the most important thing is, apart from being able to get these results, knowing where they are in the notes, not remembering them. That's not needed. Now the normal is another important aspect of a parabola, in fact for many shapes, that one would want to know what the equation of it is. So again, to remind you that the normal is a straight line which is always perpendicular to the tangent. Well, as we show here, we've got a tangent shown as the dotted line at the point at squared 2at, and we know that the gradient is 1 over t. Because the normal, which is this straight line, is perpendicular to the tangent, then we know the slope of that is minus 1 over this, in other words minus t. So the gradient of the normal at the point at squared 2at for any parabola y squared is 4ax is minus t, minus the parameter t. So if we now take p as any point on the normal, again the gradient of the line segment from the tangency point to p is given by this ratio, and that's minus t. And so on rearrangement we obtain this expression here. Again, not something to remember, it's a little more complicated. And now it's y plus tx is at cubed plus 2at, and you can readily check whether at least it works by first of all rearranging this to show that y is minus tx plus something, so its gradient is minus t, which is correct. But also if one substitutes for y as 2at and x as at squared, which is 1 point on the normal, which is this point here, then that again is satisfied. Similarly for the tangent, so if we go back to that, then again here one can easily check that y is equal to 1 over t times x, so the gradient is 1 over t, and again x is at squared, y is 2at, this whole expression becomes 0, so that's also satisfied. So this is the expression for the equation for the normal, where xy represents a general point on it at the point at squared 2at. The normal in Cartesian form can again be derived. It's shown here in the box, and this time, since we know that the gradient in Cartesian form of the tangent is 2a over y1, then the gradient of the normal is minus 1 over that, which is this expression. And again expressing the fact that from any point P on the normal to the point here, the tangency point, that the gradient of the line segment is given by this ratio, then clearly that's minus 1 over 2a, and on rearrangement we get this straight line. And in this case there's no advantage to try and eliminate y1 in terms of y1 squared is 4ax1 as we did for the tangent. Finally, in this section we're going to look at the equation for a chord. Now for a circle, a chord is just a line segment that joins 2 points, distinct points on the circle, and the same is true for any conic section or for any curve. So in this case I've shown the parabola, and I've taken 2 points on the parabola, P1 and P2, and I've labelled them parametrically with coordinates at1 squared and 2at1, and similarly for P2. You could equally use T and U or P and Q, which we will probably do later on. But if we keep the 2 points P1 and P2 as indexed by the subscript 1, then we can draw the line segment that passes between the two and try and determine the equation that is for the straight line that represents that line segment, where P, X, Y is a general point on it. Now first of all, in order to do that, we need to work out what the gradient of the line is, and of course because the gradient of the line passes through P1, P2, we know that the gradient of that line segment is the difference of the y coordinates divided by the difference of the x coordinates, which is this, assuming that T1 and T2 are different. In other words, P1 and P2 are not the same point. So that would be where this chord becomes a tangent. So by factorising the denominator as the difference of two squares and cancelling, because T2 is not equal to T1, we get this expression for the gradient of the chord. And then we can use that because any point P on the chord has a gradient from P1 to P given by this ratio, and of course that's just the gradient of the line from P1 to P2, which is this ratio. Again, on rearrangement and simplification, we get this as the standard form for the equation of the chord that passes through the points P1 and P2 on the parabola y squared equal 4ax at the points indexed by at1 squared 2at1, at2 squared 2at2, where those are the two parameters, T1 and T2. Similarly, if you were to index them differently, ap squared 2ap, aq squared 2aq, then T1 and T2 just become P1 and Q and PQ. Again, this is a form that we will use. You don't have to remember. You could look it up, but again, we need to understand where it comes from. Now, one interesting point to note, which is by way of a simple check, if you allow T2 to approach T1, so to get those 2 points closer, then you can see on the graph what will happen is that this chord becomes a tangent at that point. And in the expression for the equation of the chord, clearly if we allow T2 to approach T1, these two become the same thing, and so that becomes T1, and this becomes at1 squared. And of course that, as you would expect, is the equation of the tangent at the point at1 squared 2at1. In other words, we can get the equation for the tangent from the equation for the chord by allowing the 2 points to approach one another.